Today I will present the midterm update on my gated step frequency ground penetrating radar design. This project involves a hardware-based simulation, and I will also build and test the system comparing the physical implementation to the simulation-based implementation. So the main components of the GPR is a frequency synthesizer evaluation board, which comprises a phase lock loop and a voltage controlled oscillator used to generate the radio frequencies that propagate through the environment. I will use two bandpass filters, one to remove spurious frequencies generated by the frequency synthesizer and another one on the receive path of the antenna. A power splitter distributes the RF signal to both the transmit path and the local oscillator of the mixer. To amplify the receive and transmit paths, I will use two low noise amplifiers. Additionally, I have incorporated a single pole double throw switch and mixer. A low pass filter removes spurious frequencies from the intermediate frequency produced by the mixer. An analog to digital converter takes the intermediate frequency and stores it on a computer hard drive. Moreover, two Yagi antennas serve as the transducer to propagate the signal. Using AERO, I modeled all the components. I further need to model the VCO plus PLL subsystem, which will allow me to generate plots for the expected spurious frequencies and obtain noise factor and signal-to-noise ratio plots to better understand the effectiveness of the design. Here are plots showcasing the intended chirp signal generated from the ramping function of the frequency synthesizer evaluation board, the expected power of the frequencies generated by the frequency synthesizer, and the mixed signal from the local oscillator frequency synthesizer path and the RF receive path. Here are plots showcasing the gain of each component. I showcase the evaluation board's proprietary hardware from Texas Instruments, which I set values for the inner subsystem, allowing the frequency synthesizer to get the desired output. Further ramping settings will be needed for the chirp signal to be generated. I designed and simulated a 10th order Butterworth low pass PCB. I simulated the components and of the using actual surface mount device, high Q, and capacitor values that I have. Here I showcase the filter's idealized response and the actual response based on the values that I have. Below is a two-layer PCB outline, which I will send a DigiKey to be fabricated. I use AERO's proprietary software and PCB characteristics to determine the lengths and widths of the microstrip lines. Now I need to simulate the 3D EM waves in the AERO and then output the characteristics and put them into the system level simulation. The low noise amplifiers, switches, and frequency synthesizers have voltage and current limits. To ensure that the currents are in safe use, I will use a linear regulator with feedback current limiting circuits that use NPN transistors, op amps, and Zener diodes. This design showcases the LNA circuit I created at LT Spice. I wrote code that operates the single pole double throw switches, and timing has been exaggerated for demonstration. I cut and crimped all the coaxial cables and I tested them with a spectrum analyzer.